All right. Any questions on anything in the class at all? How things are going? No one showed up at office hours on Wednesday after class. That's fine. But if there's any questions, this is a good time to ask. Or if there are any, or obviously you could have come to office hours. But any questions on how the class is run and stuff like that? Look for a Canvas announcement at some point soon from me, because there are going to be a handful of videos and stuff that are associated with what's going on with what we're teaching right now. But as I mentioned, it's not really a useful use of our in-person time for me to show the videos. Under normal circumstances, I would have, but probably not this year.
Mitchell, I was wondering if there's any sort of updates on the exam dates.
There's not. The exam dates are probably going to be during week. If I recall correctly on the syllabus, it was week 6 or 7, I think. It might have been 7,
yeah.
if I'm recalling. And so that's like still about 3-4 weeks away, if I'm not mistaken. So I haven't planned it. It's going to be sometime that week. We're going to try and find a 3-hour block of time that works with everyone. And I will try to make it synchronous. Although if there are really, really strong conflicts with time zones and stuff like that, then we'll try and accommodate everyone as much as we can.
Okay. Thank you.
Yep. All right. So where were we? We were talking about conservation laws, right? And we talked about conservation of mass, and that gave us the continuity equation right here. And we're also talking about conservation of momentum, and that gave us 3 different equations here for Cauchy's momentum equation, right? And what we found was that this gave us 4 different equations, but there were 13 different unknowns that we have, right? We then talked a little bit about conservation of angular momentum, referred you to the textbook, it's somewhere in there. And that allows us to eliminate 3 of those unknowns because the stress tensor is symmetric. And so again, we have 4 equations for 10 different unknowns. And so definitely not enough stuff to actually, to uniquely figure out what the solution to a fluids problem would be. Okay. Today, we're going to figure out how to deal with that. Yesterday, we talked a little bit about deformation, and we introduced these concepts here of a strain rate tensor and a vorticity tensor that comes about because it turns out the velocity gradient is really what matters the most in terms of defining what the in terms of how a fluid is actually deformed and how like 2 points when moving along a fluid are going to move relative to one another. Okay? And so the reason why we spent all that time yesterday talking about that is because the way that we resolve this issue, that we resolve this issue of too many unknowns and not enough equations is using constitutive equations. Okay. So constitutive equations are sort of a different class of beast than what we've been talking about so far, right? So far in the class, we've talked a lot about conservation equations. And conservation equations are based on fundamental physical principles. As in, momentum is always conserved, or mass is always conserved, right? It doesn't matter what you're dealing with, what system you're playing with, or something like that. That's always going to be true no matter what, right? When we talk about constitutive equations, those are for specific materials. Okay? In other words, someone went out and did an experiment and determined that this particular material obeys this particular equation. Okay? They're based on empirical observations. Okay. And this is actually going to be a really short unit because there's actually only one constitutive equation that we're even going to write out mathematically. Okay? Constitutive equations allow us to relate stress and deformation in a material. And you guys probably could have guessed that the one constitutive equation we'll write is for Newtonian fluids. Okay? That equation looks like this. Okay? Nod your heads on Zoom or here, I guess, if you've heard of a Newtonian fluid before and have played with and have thought mathematically about Newtonian fluids. Now nod your head if you have seen this equation before. Good. So very few, right? And that's just because this is a really overly complicated way of writing the constitutive equation for Newtonian fluids. I'll get to maybe something that looks a little bit more familiar to you guys in just a second. But just to define a few things in this equation, you guys have seen most of these, right? You know what tau is. That's the shear stress. That's the shear stress tensor, the viscous stress tensor, right? This is the strain rate tensor that we talked about on Wednesday. Okay. Mu is a phenomenological constant. You guys have probably heard about this before. That's called the shear viscosity. And for most of what we're going to be dealing with in this class, this first term is all that matters. Okay. In some cases, Newtonian fluids, with Newtonian flows, you have to worry about this kappa. That kappa is called a bulk viscosity. But the reason why we don't typically deal with that in this class is because we're talking about incompressible fluids. And when we have incompressible fluids, del dot V is equal to 0 by continuity, right? And so this term goes away. In other words, the bulk viscosity here, this shear viscosity, you can think about sort of phenomenologically as like how much the fluid resists shear deformation, right? How much, or in the colloquial parlance, that's how much does the fluid resist flow, right? Kappa here is how much does the fluid resist expansion or contraction. And so if you have a compressible fluid like a gas or something like that, or maybe something supercritical or something like that, then there could potentially be parts of regions of flow where the fluid would actually expand or contract and change its density. And then kappa tells you how much it resists that. But for this class, we're going to be dealing with basically purely incompressible flows. And so for incompressible flows, then this equation reduces down to this. Okay. And if you recall, let me just point you guys to that real quick. When we were talking about deformation here, the strain rate tensor is defined as 1/2 of the velocity gradient and its transpose, the sum of those two, right? And so if I were to keep this equation here in mind, right? If I were to take this and plug it into what we have here, then what we get is the 1/2 cancels the 2, and so you get mu times del V plus del V transpose. Okay. Or in index notation, you get that tau ij, the elements of the viscous stress tensor, is equal to this. I don't know why my pen's having issues with straight lines today. But like that, okay? And now nod your heads if you have seen things that look a little bit more like this over Zoom or in person, right? Perhaps you haven't seen index notation before, but you've almost certainly, if you've taken a fluids class, seen something like tau xy is equal to the mu times the derivative of vy dx or vx dy or something like that, right? That's probably what was introduced to you in an undergrad version of this class for that, and you were called, and that was called Newton's law of viscosity. right? And so this equation right here, it's a tensor equation, right? A tensor has 9 components. And so this equation right here is actually 9 different equations. But of course, we know that the stress tensor is symmetric, as we talked about. And so this is actually, since it's symmetric, then it's actually just 6 different equations, right? And so basically, this is 6 equations, right? And so we have the 4 equations from conservation. From conservation laws. Okay. And so now we can solve for 10 unknowns. Okay. And that's basically how we actually do fluids problems, right? We use the continuity and momentum equations, Cauchy's momentum equations that we talked about on Monday, that we derived on Monday, right? And then we use these constitutive relations that relate the shear stress tensor to the strain rate tensor that we talked about on Wednesday. And then that gives us exactly the right number of equations to actually solve for the 10 unknowns that we have, right? Now, typically, you go one step farther. And so we don't talk about solving for 10 unknowns because, in real life, we care much more about the actual fluid flow and the velocity fields and stuff, and not the actual unknowns, or not the actual shear stress tensor variables, right? And so we just plug everything in order to eliminate. So we have 4 equations or 4 unknowns. Okay. Here's how we do that. We're just going to plug everything into the momentum equation. Okay. If you recall, Cauchy's momentum equation looked like this. That. And so now we can plug this equation right here into tau, and we'll get something that looks like this. So I won't write this sort of stuff again, but it's all the same. And now there are 2 terms in this equation up here, right? And so when we plug it in, we get 2 terms. We get a mu d squared vi dxj plus mu d squared vj dxj .
Wait, do y'all not hear anything?
Can't hear more.
No, I can't hear anymore.
Professor Wong, we can't hear you.
I think he's saying his battery's dead.
How about now? I don't know how we went through an entire battery in like 48 hours, but let's see how this goes. Everyone can hear me now, right? Adrian in the classroom obviously can, so yeah. All right, where did you stop hearing me?
Like the equation before you got to the current line that you're at.
Okay, so somewhere around here, right?
Right.
All I was trying to say is that to plug this guy into the shear stress tensor, you just have to take a derivative with respect to xj, right? And so the derivative of this first term with respect to xj is d squared vj dxi dxj. That's what this is. I wrote dxj dxi, but same thing, right? And then the second term is d squared vi dxj dxj, and that's where this term comes about, right? And so we can simplify, it turns out, one of these terms. This term I'm going to keep the same, but this next term here I'm going to rewrite. I'm going to rewrite this like this. Okay? Because it turns out I can take the order of the derivative however I want, right? And so I'm going to take the derivative of vj with respect to xj, but perhaps you guys recognize what this means. Can anyone point out what this means over Zoom? Or I guess, Adrian, you can shout if you want to, but then I'm going to have to repeat for what you say to everyone, so. All right, someone over Zoom, sorry, just because most of you guys are on Zoom right now. What does this, does anyone recognize what this term actually means?
That's the divergence.
That's the divergence of velocity, right? And we know that for an incompressible fluid, the divergence of velocity is 0. So this term actually goes to 0, right? Because del dot v equals 0 for incompressible. Okay, and so then what we're left with in let's say non-index notation is this equation, which I like to say is really an equation that we can all get stoked about. Okay, and that's because we have a special name for it. It's called the Navier-Stokes equation. Thank you. Nikhil said, I hate that pun. All right, if you want to see this in Dean, that's equation 659. The derivation is pretty similar to what I actually wrote out. Okay. And so now that we have this, again, this is a vector equation for velocity. So that's 3 equations. Okay. And then add that to our continuity equation, which never changed. Okay. And so what we have is 4 equations, right? And we have 4 unknowns. Those unknowns are velocity, our velocity, and the scalar pressure. And so we have a fairly well-defined system here, and we should be able to solve it, right? Okay, one thing before I actually start solving stuff is that I want to point out that this is for Newtonian fluids. One of the videos I'm going to send out is going to talk a lot about non-Newtonian fluids. Okay, and there's a whole field. My research hardly has to do with this as well, right? But there's a whole field about what do fluid flows look like when you have things that don't behave like Newtonian fluids. Newtonian fluids would be things like water or whatever, right? And so you'll see this nice video online about this. Okay. Was there? Sorry, did someone unmute themselves and ask?
No, sorry, that was me. Does this class cover anything about like rheology or anything like that?
No, there is a class that's offered every other year by Wes Burkhardt that actually talks about rheological behaviors of fluids and stuff and how to actually do rheometry and stuff like that.
Okay, thanks.
Okay. Trust me, there is so much to talk about even when we're dealing with Newtonian fluids. And so given that the class is 10 weeks, there's really not enough time to cover non-Newtonian stuff. I will point out, though, that some of the homework problems might actually ask you to explore what happens to flows when you have non-Newtonian fluids. I believe one of the homework problems this week actually does. Okay. All right. And so just look out on your email for something like that. Okay. So these are the 4 equations that we're going to have to deal with. Right before class, I took the liberty of writing them all out. That's what they look like. Okay. You can copy these down in your notes if you want, but all this is recorded and the notes are shared with you, which is kind of nice. Okay. Normally in class, I would have like spent 5 minutes actually writing this out on the chalkboard and stuff, but now we don't have to. But the reason why I spent all this time writing them out is to basically show you that even with Newtonian fluids, look at how complicated these equations are, right? You see the 4 different unknowns here, Vx, Vy, and Vz, and P, and you see the 4 different equations, but they get really, really complicated really, really quickly. And so if you can solve these equations in the most general sense, or even prove that, that there is always a unique solution to these equations, regardless of what boundary conditions and stuff you can put out and stuff, you get $1 million. Okay, that's one of the unsolved like $1 million Millennium Clay Foundation prizes and stuff. And I don't think we're going to get to that in this class, right? But I just want to throw these out there to show you how, to give you an appreciation of how difficult some of these solutions can be. And basically, for the entire rest of this class, we're going to talk about different cases of solving the Navier-Stokes equations for different flows that you might see in either your research, in real life, or perhaps giving you some analogies for other situations that you might encounter and stuff. Okay. Part of the reason why these equations are so difficult to solve is because these are coupled nonlinear partial differential equations, right? Coupled as in you have to solve 4 equations simultaneously for 4 different variables. And they're nonlinear because you actually have some of the unknowns multiplied with one another, especially this stuff over here, these 9 terms right here, right? You have velocities multiplied by velocities here. And when things get nonlinear like that, solutions get very chaotic and get really, really complicated very quickly. So I'll just say that these are very difficult to solve. And that's where the $1 million comes in. Okay. Now, for the next couple weeks, we'll be dealing with simple flows. Okay. And when I say simple flows, I mean things that have really nice geometries, flows that are slow enough, and stuff like that. What you'll find in those cases is that you can actually find exact solutions. Okay? But even in those cases, sometimes the math can get really tricky, right? Because, you know, maybe some of you guys have taken undergrad classes with me or have taken some more advanced math classes and stuff, might know how to solve partial differential equations, but solving partial differential equations is not a piece of cake either, even if they're linear. Okay? And so I'm going to warn you over the next couple weeks, I'm going to introduce some math for you guys that allows you to solve those sorts of things. It's going to get pretty tricky very quickly. Okay? And then after the next few weeks, we're going to be dealing with more complex situations. And for those, there's really not much that we can do besides approximate. Okay, and so even if you don't deal with fluids in whatever research you want to do while you're here at Northwestern or beyond, hopefully some of these approximation techniques can inspire some things that you might think about. Okay, or of course, you could also use numerical solutions. And of course, in a lot of research that you might do, you might also do numerical simulations and stuff like that. Again, maybe not specifically with dealing with fluid flows, but maybe some of the same principles might apply. It could be useful here. Okay, but we're probably not going to be able to get to too much stuff about numerical solutions in this class yet either. Okay, but for now, let me just give you a general recipe for solving these equations, or just solving fluid flow problems for basically the rest of this class. Okay, it's going to be very detailed. This is the stuff, some of these things are going to appear obvious, but I want you guys to think about all these things when you're actually dealing with your fluid mechanics problems, okay? This first one, of course, is just to write down the equations. if you don't do this, sometimes you forget different terms that could actually matter and stuff. For instance, let's say you're dealing with a non-Newtonian fluid. You might write down the wrong equation or something like that, or you might forget a term or something, right? The next thing that you should always do is write down the boundary conditions. Okay, if you've taken a fluids class before, you know that an equation doesn't really make sense without boundary conditions, right? And then perhaps the most important thing to do is to think about your situation right here, right? And think about different ways of simplifying the problem and you know, different approaches that you might use to solve it, right? So for instance, what form of the solutions are expected? Expected, right? Can we say some of the terms go to 0? And the first term, the first problem that we're going to be dealing with in just a second, we're going to be able to eliminate all of these terms. And in fact, especially for the next couple of weeks, we're going to find that a lot of the times we're going to actually just write down this long set of equations, or not even write down this long set of equations, because we're just going to eliminate some of the variables offhand, right? Are things like the velocity or the pressure constant with some coordinates, right? So like, maybe there's a situation where the whole problem is invariant in one direction or something like that. Or maybe you're dealing with like a rotational flow or something, and it makes sense to use things like curvilinear coordinates, cylindrical coordinates, and stuff like that, right? We'll introduce that a little bit later on in the class, although I suspect most of you have seen cylindrical coordinates. Maybe you haven't seen it in this vector calculus stuff that we talked about yet, so we'll try and get them on the same page, right? And then, of course, there's ways of simplifying or to transform the equations into equations that become easier to solve. And we're going to spend a lot of time talking about how to deal with that. Okay. Once we've done that, now we have to actually do what we came to do, which is to actually solve the differential equations. There are various techniques that we're going to be dealing with, that we're going to show to allow you to do that. Of course, in many cases, especially later on in the class, we might not actually be able to do that. So if we can't, then we have to approximate. Approximate. Okay, and to do that, in many cases, we talk about in fluid mechanics. If you've taken a fluid mechanics class, you probably have heard about all sorts of different dimensionless groups and stuff like that allow us to think about how much do different terms in the Navier-Stokes equation compare relative to one another, and can we call some of those terms negligible, right? So are some terms negligible? Okay. And then perhaps even more important, but related to step 3, is we need to evaluate our solution. Okay. So for instance, does it make sense? And when I say doesn't make sense, you think about, like, is the flow actually moving in the right direction as to what you expect? Does it satisfy the boundary conditions, right? You might end up doing like a whole bunch of complicated math and get like this solution at the very end that you don't even recognize, or it might just be like a sum of different functions. We'll get to a lot of those in the future, right? If you have, and you might have no idea what that even physically means. Can you plot it? You guys have some experience in your homeworks by plotting these sorts of things, both in terms of vectors or just if you have a unidirectional flow, then just a normal XY 2D plot or something like that. Can you show that that solution actually satisfies the boundary conditions, right? If it doesn't satisfy the boundary conditions, then clearly you've made some sort of egregious error going on, right? And then, of course, if you have to approximate, you need to think about, are the approximations valid? Okay. And so let me get into this then. We'll do for the rest of this class, we have maybe 20 minutes or so. I'll see how far we can get into our first flow problem. It's perhaps something that you've seen already. It's a common undergraduate problem, for instance. And this is just fluid flow down a wall. Okay, nod your heads if you've seen this sort of problem before. Cool. We'll do it in sort of this new framework that we have, and also trying to be as rigorous as possible, and because it's a great way of explaining all the different concepts that we've talked about so far. Vectors, tensors, stress tensors, all of that sort of fun stuff. The problem looks like this. We have a thin layer of fluid that's up against a solid surface like this under a gravitational field G. Okay? The fluid is flowing down like this. There's some pressure outside of this fluid that's equal to, that we'll call ambient pressure, so PA. And whenever we deal with this sort of stuff with flow problems, we almost always give ourselves, or not almost always, we always give ourselves a set of coordinates. And so let me define my coordinates like this. X is going to be positive in this direction, and Y is going to be positive in this direction, okay? And so we'll let our fluid have a thickness here of H. Okay, so sorry about the inverse axis here, but hopefully it shouldn't be that difficult to get everything straight. Okay, so here we go. Now, in solving our flow problems, we first have to write down our equations. Then we have to write down the boundary conditions. Okay, here are the equations. All right, I'm not going to write them down again. Let's think about the boundary conditions. Okay. You guys have probably all heard about the no-slip boundary condition, right? We're going to use that in this class a lot too. That no-slip boundary condition applies at y equals h. The no-slip boundary condition basically says that velocity is equal to 0 near a solid surface. All components of velocity are actually equal to 0, right? You can't have velocity going in the y direction because then you would be permeating the surface. That doesn't make any sense. Permeating the wall, I guess, that doesn't make any sense. And you also can't have any velocity going in x or z. Okay. The other boundary condition at y equals 0, some of you guys might call this the no stress boundary condition or something like that. We're going to be dealing with this one with a little bit more rigor. All this really says is that the velocity is continuous across an interface. Okay. And that the stress is at equilibrium. What that means is basically Newton's third law, is that all the stress vectors should cancel each other out, right? You can't have stress built up at any thin interface here, because otherwise F equals ma, m goes to really small. If F is non-zero, then a goes to infinity, and that doesn't make any sense. Okay, so let's examine the stresses actually at this interface right here, right? On the fluid side, okay, so what we're going to be asking ourselves is how much stress is the fluid exerting onto the air, right, onto the surrounding air. If you recall how the stress vector and stress tensor and stuff is defined, the force that the fluid exerts onto the air is when the normal vector points towards the fluid, right? So if we care about what's going on the fluid side, then N is equal to EY, because EY points towards the left right here. And so N has to point in that direction because we're dealing with how much force does the fluid, which is on the left here, exert onto the air. Okay. And so S of EY, by definition, is n dot sigma, where sigma is the stress tensor, and an n here in this case is EY. And of course, sigma is defined as that, right? And now we can simplify this a little bit using the dot product. We're going to take a dot product of EY with this tensor, okay? The dot product of EY and the identity tensor is just EY. Okay, the identity tensor dot with anything is just the same thing as itself, right? And so we're going to get a minus PEY here, right? Let's not deal with that for just a second here. The stress tensor has 9 different components, right? One of those components, well, it's going to be something like tau xx ex, tau xy ex ey, tau, et cetera, right? One of those components is going to be tau yx ey ex. And you can see that ey dotted with ey ex gives you an ex, right? Because ey dotted with tau yx ey ex is just tau yx ex, right? Because ey dot ey is equal to 1. Okay? And so that's going to give me a tau yx ex, right? Likewise, I'm also going to have a tau yy ey, and I'll go ahead and add in my pressure contribution to that as well. And then, of course, I have tau yz ez for the same argument as what I drew out up here. Make sense? Now, of course, I also have 6 other components of my stress tensor. But in, let's say, any of those other components, let's say I'm talking about tau xx or something, then I'm going to have ey dot tau xx ex, but ey dot ex is just equal to 0, right? And so those terms all go away. So I'm only left with 3 of those terms here, right here, okay? Now on the gas side, okay, there we're dealing with what happens when the normal vector points in the negative ey direction. Draw this a little better. In the negative ey direction. Okay. When we're dealing with a gas, we can assume that the viscosity is so small that it doesn't matter. And if the viscosity is really, really small, then Newton's law of viscosity also implies that for a Newtonian fluid, tau is also essentially equal to 0. Oops. Tau is also equal to 0. Okay. And so that means that S of minus ey still is the same here. Still the same definition, right? Ey minus ey dot sigma, and then minus ey dot negative p delta plus tau. Except tau here is gone, right? And so all we have is negative ey dot the pressure. We wrote down what the pressure is. That's PA, as we wrote down right here. Here, right? Ambient pressure times the identity tensor. And so we have PA times EY. Okay? And so if the stress is actually at equilibrium along this interface, then that means that these 2 quantities have to be negative of one another. This quantity right here, that's S of EY on the fluid side, and this quantity right here, that's S of E negative, that's S of negative EY, has to be exactly opposite one another, right? So that implies S of n equals negative S of negative n. That implies that this first term right here has to be equal to the negative of the second term right here. Okay? And when two vectors are equal, then all the different components are equal, right? We have an x component. What that suggests is that tau yx is equal to 0 because there's no ex component over here. Okay. We have a y component. Okay. Just in case you guys don't see it immediately, this tau yx comes from Newton's law of viscosity, right? That's dvx dy dvy dx. Okay. This tau yy also comes from Newton's law of viscosity, right? It's just dvy dy plus dvy dy is just twice that, and so that's where the 2 comes in. Okay. And then the z component looks analogous. All right. And so those are our boundary conditions, right? This was kind of laborious. I don't expect you guys to go through all this math for every single problem because we're already 10 minutes into our solution and we've only gotten to step 2. Okay. But what we found in our boundary conditions is that Vx, Vy, and Vz are equal to 0 at y equals h, and at y equals 0, these things are true. These derivatives have to add up to 0. These derivatives here have to add up to 0. And then, of course, the pressure in the y direction has to be equal to PA. Okay. The next step in our solution, remember, is to think about what we can do to solve, to help our solution go on, right? We might expect that, as drawn here, everything is going to be exactly the same regardless of where we are in the z direction. Okay, so we have no action in the z direction. Okay, so what that implies then is that Vz is equal to 0. Right, and all derivatives with respect to z are also equal to 0. Right. Maybe another assumption that we can make is that our flow here is steady. Right. I guess I never actually used that word when I was setting up this problem, but maybe it's a decent approximation that we can make. That implies, of course, that all time derivatives are equal to 0. Okay. We might also be able to say something along the lines of what happens at for Vy as well, right? We know from the no-slip boundary condition that Vy has to be equal to 0 at y equals 0, right? And we know just from how the problem is set up that there can't be a velocity in the y direction at y equals 0 either, because then this interface will be moving, right? And so if we say that Vy is equal to 0 at y equals 0 and y equals h, then maybe that implies that Vy is equal to 0 everywhere. Okay, well, we can think about relaxing that assumption and think about evaluating that later on in the problem, right? And now I'll try and flip back and forth very quickly, but this was the original problem right here, right? Using those assumptions that we just wrote down, that all of our time derivatives are 0 and all of our z derivatives are equal to 0, and our Vy is always equal to 0, then continuity gets to just be dvx dx is equal to 0, right? So what we have here is that continuity implies that dvx dx is equal to 0. Okay. The x component of the Navier-Stokes equation is going to now look something like this. We had all these other terms in the front of the Navier-Stokes equation, like this. This was the x component of the Navier-Stokes equation, right? But no time derivatives. Okay. We know from continuity that this is equal to 0 because we just showed that dvx dx is equal to 0, right? There's no vy. There's also no vz. So these terms all go to 0, right? These terms are possibly still there. But then for all these terms, we know that all of these others, like this term has to be 0 because dvx dx is equal to 0. And this term is 0 because there's no z component either, right? And so the x component of the Navier-Stokes comes down to something like this. We get 0 is equal to minus dp dx plus rho gx. Or in this case, actually, we wrote down what our g is. Our g right here is just equal to g times e of x, right? It's just g, a constant g going in the x direction. So it's just g times e of x. And so gx is just equal to g, 9.8 meters per second squared, for instance, right? And then plus mu, the only thing we were left with in that set of 3 terms is this. You can apply similar logic to the y component and the z component of the Navier-Stokes equation, and you get this. Okay. What we find here, I guess the x and the y and the z components of the Navier-Stokes shows us that pressure is not a function of y and is not a function of z, right? So I'll say yz of Navier-Stokes implies that pressure is only a function of x. Okay. We also find that Vy is only a function, or Vx is only a function of y, right? Notice how there's only a derivative with respect to y in terms of Vx here, right? Okay. Or another way of putting this is, we know that it can't be a function of z because there's no action in the x direction, right? And Vx also can't be a function of x because the derivative with respect to x is equal to 0. And so Vx is only a function of y, right? Okay. But we know that at y equals 0, we know that pressure is equal to PA, right? That's what we showed right here. This boundary condition right here allowed us to show that because dvy dy is equal to 0, as we showed, right? From continuity, right? Or we showed that vy is equal to 0 everywhere, so therefore dvy dy is equal to 0, right? And so what we showed here is that pressure is equal to PA at y equals 0, right? This is true for all x, right? Because this is true throughout this entire boundary here at all values of y equals 0, right? And so if that's true, then that means pressure is only a function of x, but pressure is equal to PA for all x, and so therefore pressure is a constant. Okay? Does that kind of make sense to you guys? It's sort of our way of logicking out what, and allows us to eliminate one of the 4 unknowns that we have in our 4 equations here, right? The idea is that pressure, we know from these equations, is only a function of x, but So in other words, pressure doesn't change when I move up and down this wall right here. It's always going to be, it's only going to be a function if we move up and down this wall. But we know that pressure is always equal to PA as well when we move up and down this wall. And so pressure is just going to be PA everywhere in this whole thing. Okay, the pressure is just always going to be ambient. It's perhaps an obvious fact that you guys might have intuited already, but that's great. Now we mathematically are able to actually show it. Okay, and it comes about just because of the subtleties of all these sorts of different of all these different tensor and vector relationships. Okay. And so our equations now reduce to this. This is the only equation that really is kind of interesting to even solve at this point, right? We get that d squared vx dy squared is equal to minus rho g over mu. And we end up with two boundary conditions now. Okay. There's a boundary condition 1, that vx is equal to 0 at y equals h. Okay. This comes about from the no-slip boundary condition. And we also have another boundary condition that comes about from this. Okay. That we spent a lot of time actually trying to derive. But what we get is that because Vy is equal to 0 everywhere, right, then this boundary condition now reduces to mu dvx dy is equal to 0, or just dvx dy is equal to 0. Okay. I don't expect you to go through that much trouble to actually figure out everything there is to know about this problem and everything. Okay, to go through that level of rigor and stuff. But this perhaps shows you that mathematically from the Navier-Stokes equation, we can basically get down to a set of equations that now this looks really, really tractable to solve by just applying some very basic assumptions and some very basic mathematical manipulations and tensor manipulations and stuff like that. For instance, hopefully prior to or at 3:30 or something, you guys have not actually thought about how stresses actually happen at an interface like this, right? There's another video that I'm going to upload sort of in tandem with a non-Newtonian fluids video that talks about what happens if the stresses are not at equilibrium at a surface, or specifically if this equation is not necessarily true at a surface. This happens when we have to deal with things like surface tension and stuff like that. Okay, and so the stuff that we wrote here is sort of more general and is sort of a general framework for solving these problems. But again, I don't expect you, especially if you're time limited on an exam, or it's like 4 a.m. and you really want to finish the homework set or something like that, I don't expect you to go through all of these laborious steps. But hopefully this gives you a picture of how we deal with all these things. Okay, I'm going to stop here. This is the end of step 3. Once we pick up on Monday, we're going to actually solve this problem and then actually kind of examine what happens to the solution once we think about it. Okay, any questions?
I have a quick question.
Yeah.
Did you say that Vy equals 0 everywhere is an assumption that we could relax later on?
Yeah, I'll talk about a little bit on Monday, like what scenarios would we potentially relax. All of these assumptions actually are assumptions that we might need to relax later on.
Okay,
You
because
can imagine
that is a condition for the continuity equation to derive that Vx is constant. Like
yeah, exactly. So normally the continuity equation is dvx dx plus dvy dy plus dvz dz is equal to 0, right? But it's the assumptions that we applied where all derivatives in z are equal to 0, and then all derivatives in y, and then vx vy is equal to 0. That allows us to say this. In previous incarnations and other classes that you guys might have seen, one of the initial assumptions that you might have made is just that everything is invariant in both z and x, right? You might have said, oh, it doesn't matter how far along the wall we actually are, everything looks exactly the same. Nod your heads if this sounds familiar to you at all. Or just intuitively, you might think, oh, you know what, it doesn't really matter how far along the wall. Notice how we never had to make any sort of assumptions about what happens in the x direction. That assumption actually is completely unnecessary. It comes about because of the continuity equation and all these other assumptions that we made. Right. Any other questions? Okay. Hope everyone has a good weekend. I will see you on Monday.
Have a nice weekend. Thank you.
Yep. See ya.